Hello everyone, I'm Wang Chao from the National University of Singapore. Today is my pleasure to introduce our recent work, quantum random number generation with uncharacterized homodyne detection. The motivation of this work is that we would like to come up with a QRNG scheme based on homodyne detector, but we don't want to characterize the functioning of the homodyne detector during the experiment. So there are several reasons for doing so. First of all, we know that the homodyne detector has some appealing features for quantum cryptography and quantum information applications, such as it is chip compatible, it has compact size, it has low cost, and it can operate in the room temperature. However, it is also known that the characterization or full characterization of the homodyne detector can be difficult in practice. For example, the cultural measurement using homodyne detector is valid only in the strong local state limit. Practical homodyne detector has finite common mode rejection ratio, CMR. Balancing of the homodyne detector may drift over time during the system running, so on and so forth. So these are the reasons why we would like to do a QRNG with uncharacterized homodyne detector. So in terms of the random certification, we come up with a security analysis, which comprises two main parts. The first part is the semi-definite programming method proposed by our group in 2019. And the second part is the entropy accumulation theorem, EAT. So the details of the security analysis has been already presented by our group member William in last year's Qcrypt, and also we present the details of analysis in the archive paper. You can find it online. So here I just have a brief introduction of the random certification. So basically, for the first step, we use the overlap of the states and the experimental statistics as constraint to run the SDP to bound the guessing probability of eavesdropper, which corresponds to eavesdropper's single run information. So in this step, with our SDP method, we don't require to know the POVM of the measurement devices. So we just treat the measurement device as a black box. With the eavesdropper single run information, in the step 2, we use the EAT method to bound the conditional smooth mean entropy, which corresponds to the overall extractable randomness of our system. With this security analysis, our protocol is secure against quantum site information, which means that we can allow the uncharacterized measurement device homodyne detector to be entangled with eavesdropper outside the QRNG system prior to the execution of the QRNG protocol. In order to test the feasibility of the protocol, we set up a fiber optical experiment system as shown in the middle of the poster. Our experiment system comprises 3 main parts. The first part is the quantum state preparation. The second part is the quantum state measurement, and the third part is the system control and data processing. In the quantum state preparation part, we have a laser source to generate coherent state. The beam splitter split the laser into 2 passes, one for quantum state preparation and the other for local oscillator. In principle, our protocol allows any form of quantum state preparation, but in practice, we choose to implement QPSK and QM16 for the convenience of the experiment. In the quantum state measurement part, we have a phase modulator to choose the basis for homodyne detection, and a beam splitter, a pair of photodiode, current subtraction circuit, and the amplification circuit to work as a homodyne detector. Since our protocol does not require to characterize the homodyne detector, any errors in basis choosing, phase modulation, the beam splitting, balancing, and so on and so forth does not require to be perfect. The third part is the system control and data processing. In this part, we need to assume we have trusted and private random seed for quantum state preparation and basis choosing in the homodyne detector. And we also need to do entropy extraction to get the final random number generation. So in our case, so in our system, we adopt a complementary modulation scheme and two more coherent state for quantum state preparation to ensure the signal integrity with any system settings X and Y. Another requirement by our protocol is that we need a relatively high quantum efficiency of homodyne detection to obtain a positive random number expansion rate. In our experiment, two efforts has been made to achieve this target. First of all, we adopt a pair of high efficiency photodiodes for 1550 nanometer and develop high efficiency coupling system to reduce the coupling loss. Second, we use a high gain and low noise amplifier for the current to amplify the subtractive current. So the overall efficiency of our homodyne detector is measured to be 91.7% at 1550 nanometer, and the clearance of a homodyne detector with 10 milliwatt local oscillator input is measured to be 16.94 dB. Our system works at a frequency of 2.5 megahertz, and the final result with QPSK modulation format is shown below. Here we also provide the simulation result of our protocol based on QPSK modulation and QAM16 modulation with different number of system executions from 10 to the power of 10 to 10 to the power of 12. Also the asymptotic key rate. That's all for my presentation. If you have any questions regarding this work, you can contact either me or William via the following email address. Thank you so much for your attention.